The goal in this video is to find any local extrema, meaning local maximums or local minimums, or these could be also called relative maximums or relative minimums when we're given a function, but we're going to be utilizing the second derivative test to figure this out. So the first thing we need to do is we're going to be taking the first derivative of f of x. But to do so, it's going to be a little bit more convenient. Instead of using the quotient rule, we can simply use the power rule as long as we rewrite that fraction. So we can say this is 5 plus 3x plus 27, and then we'll make this, instead of x to the positive first in the denominator, let's move it up to the numerator. This will allow us to use the power rule. All right, so next, let's take the first derivative. The derivative of our constant 5 is going to be 0, and then we have 3 is the derivative of 3x. And next, we're going to say the 27 comes along because it's a constant, but the derivative of x to the negative first power, you're going to bring the negative 1 down and reduce the exponent by 1. So negative 1 minus 1 more is going to make negative 2. So our first derivative is 3 minus 27 x to the negative second power, or 3 minus 27 over x to the positive second power. All right, so we found our first derivative. Now what we want to do is locate any values where our first derivative is either undefined or equal to 0. Okay, so in this case, what we can do is it's going to be undefined at x equals 0, because if we plugged in 0 for our x value, that would be a problem. We can also set it equal to 0 and try to solve this down to find any other critical values or critical numbers. So the first thing I would probably do is add the fraction to move it to the other side. This gives us 27 over x squared equals 3. We can't solve for our variable while it's in the denominator, so let's multiply both sides by x squared to move it out of the denominator. These will cancel out on the left-hand side, making a 1. So we have 27 equals 3x squared. We can make this into a power equation by dividing both sides by 3. So we have x squared equals 9. All right, to solve this the rest of the way, we're going to get rid of our square by applying the square root to both sides. When we apply the square root to both sides, we need to remember to use both a positive and a negative. All right, so that gives us x equals positive 3 and negative 3 for two more critical numbers. All right, next what we want to do is, with the second derivative test, you're going to need to apply the power rule again to take the second derivative. I'm going to use this version with the negative exponent of my first derivative. So the second derivative is going to be f double prime of x will be the derivative of 3 is going to be 0 because it's a constant. The minus 27 can come down. And then the derivative of x squared is negative 2 x to the negative third power. Reduce the exponent by 1. All right, this means the exact same thing as if you wanted to write this with a positive exponent, we can do negative 27 times negative 2 makes positive 54 over x to the positive third power. All right, now what we want to do is we want to actually test each one of these critical numbers in the second derivative and determine whether it's going to be positive or negative. All right, we don't really need to worry about the x equals 0 because the original function was not defined at x equals 0. Therefore, it means it can't be a point on our graph, so it can't be a maximum or minimum. All right, our other values that we do need to test were when the derivative equaled 0, so that was positive 3 and, negative 3. So f double prime of positive 3, f double prime of negative 3. So we have 54 over positive 3 cubed. What we really care about is that this is going to turn out being positive. All right, and then when we plug in 54 over negative 3 quantity cubed, that's going to be negative. All right, so when our second derivative turns out being positive, that means it tells us about the concavity of the function at that particular value. So this is going to be concave up. Concave up is going to look like this. That also indicates that we're going to have a minimum at 3. Okay, next up we got a negative. When we plugged in a -3, that's going to indicate that our graph is concave down. Concave down has this sort of look going to it, and that's going to be a maximum at an x value of -3. The last thing that we need to do is actually locate where the maximum and where the minimum are at. So to do that, we're going to complete these, make them critical points. And what you need to do is take these x values that we found, 3 and -3, and we're going to go back to the original function and plug them in there. So the original function, we have f of 3 is going to be 5 plus 3 times 3 plus 27 over 3. This works out to be 5 plus 9 plus 9 more. So we're going to get a positive 23. So the critical point is 323, and that's going to be a minimum, a local or relative minimum. Whereas when we plug in the -3 into the original function, we have 5 plus 3 times -3 plus 27 over -3, which simplifies to say 5 minus 9 more, which is going to be -13. Therefore, giving us a critical point of -3, -13, and we already determined by the second derivative test that that was going to be a maximum, local or relative maximum at that point. All right. We actually, be careful on this, we say that the maximum is going to be -13, and it occurs at a value of x equals -3. And you may be saying when you look at this, hey, 23 is bigger than -13. Shouldn't that be the maximum? But that's not really how this works, because we are dealing with kind of a strange looking function here from the very beginning, that we don't care these two numbers compared to one another, the 23 and the -13. It's based on the second derivative test. And if it turns out positive, it's going to be concave up, therefore giving you a minimum. If it turns out being negative, it's going to be concave down, therefore giving you a maximum. All right, I hope this helps out, clarifies a little bit of the second derivative test. Good luck as you're trying to find these maximums and minimums.